This is the 22nd video in our series on Lie algebras, and today we're going to talk about a really important object attached to a Lie algebra, and that's called a Weyl group. Well, actually it's attached to a root system of a Lie algebra, but we'll see that the root system of a Lie algebra is unique. So actually, you can think of it as being attached to a root system or a Lie algebra. Okay, so let's look at our definition. So say we've got a root system for an inner product space E. We'll call that root system R. Then the Weyl group of R is, well, we'll call it W or W of R. And it's going to be the group that's generated by all of these S alphas. And let's recall that those S alphas were reflections about a hyperplane that was normal to the vector alpha. And let's also recall that these S alphas permuted the roots. But that means that W is a subset of the group of permutations of the roots. But we know that root systems are finite, meaning that this group of permutations is finite, and thus the Weyl group is also finite. Then let's look at this other subgroup of the Weyl group we'll call it W0, and it's going to be the subgroup that's generated by these hyperplane reflections S alpha, where alpha comes from a base, or it's like a basis element of the root system R. Well, actually, W naught is equal to W. In other words, the whole Weyl group is generated by these reflections at the base elements, but we're going to prove that a bit later. But we will use that result to explain this example. So let's recall the root system of the Lie algebra SL3. It had 6 vectors. So it had plus minus alpha 1, plus minus alpha 2, and plus minus alpha 1 plus alpha 2. Let's also recall that the reflection through the hyperplane of a vector normal to alpha is given by this formula right here. And then also we had the following picture of the root system. But just by the geometry of the reflection about the hyperplane, we can immediately see that S alpha 1 will take alpha 1 to minus alpha 1, because the hyperplane normal to alpha 1 is like this right here. It's like a vertical line. But that means it takes alpha 2 to alpha 1 plus alpha 2, and minus alpha 2 to minus 1 minus alpha 2. And then, well, you can see something similar for S alpha 2. And then quickly, you can calculate the composition as well. And I've just done one example of the composition. So if you plug alpha 1 into S alpha 2, it goes to alpha 1 plus alpha 2. Then you plug that into S alpha 1, you get alpha 2, meaning the composition takes alpha 1 to alpha 2. And then similarly, it'll take alpha 2 to minus alpha 1 minus alpha 2, and that'll go back to alpha 1. And then you can actually check that, well, this actually has order 3. So it cubes to the identity, which we see from this picture right here, and I guess from the geometry as well, because we know that compositions of reflections are always rotations. And if we're exhibiting this maybe triality or 120-degree reflection here, then that means it has to be true everywhere. But that means that this Weyl group of SL3 is generated by 2 elements of order 2, those 2 hyperplane reflections, and those 2 elements of order 2 have a product whose order 3. But there's exactly one group that has that kind of generation data, and that's the group S3. And in fact, a bigger result is that the Weyl group for SLN is in fact the symmetric group SN, but we won't prove that today. We may or may not prove it in the course of these videos. Okay, so now let's get into the results of today. So the first result of today is as follows. So if alpha is one of the elements of the base for our root space, our root space, then S alpha, that hyperplane reflection, permutes the elements of, well, the positive roots except for alpha. Let's recall, by the definition of the positive roots, the basis elements are most definitely positive roots because, well, they're sums of things with only positive weights to the linear combinations, and also, well, only one of those positive weights is non-zero and it's equal to 1. And let's notice that we do have to exclude alpha here because S alpha of alpha is minus alpha, which is in R minus. Okay, so let's get going. So what we want to do is take something from this set. So in other words, it's an R plus, but it's not equal to alpha. But what does that mean? Well, that means that we can write beta in the following way. So I'm going to write this as the sum over all gamma in B, where C gamma is bigger than or equal to 0, and here we have C gamma times gamma. So remember, it's an R plus, but it being an R plus means that we can write it as a combination of these base roots with the weight bigger than or equal to 0. Obviously, like one of those has to be non-zero. That's pretty clear. Okay, so now let's do the calculation. So we'll do S alpha attacking beta. And I guess what we want here is for S alpha attacking beta to pretty clearly be in R plus. That's what this result is saying right here. So that means we're going to get this sum over all gamma in B, where this C gamma is bigger than or equal to 0. And then we'll have C gamma of S alpha gamma. So something like that. And now we can apply the formula for S alpha applied to gamma that we saw on the last board. So that's going to be the sum over all gamma in B. We've got C gamma bigger than or equal to 0. And then this is going to give us C gamma of, and then we'll have gamma minus this angular defined, or this angular bracket inner product of gamma with alpha, and that's in the alpha direction. And now I'm going to split this apart into some pieces. So notice that I can split this apart into this sum as gamma is all in B and this C gamma bigger than or equal to 0. And then here we're going to have C gamma in the gamma direction, and then minus, well, it's going to be a bunch of other stuff that I'll just put in this big box times alpha. Okay, but now I'd like to observe that this number right here is always bigger than or equal to 0. And in fact, since beta is not equal to alpha by this condition right here, then that means that there exists some gamma not equal to alpha where C gamma is strictly bigger than 0. But that means that the weight of this gamma vector, this special gamma vector, which maybe we could decorate that with gamma naught. So the weight of this gamma naught vector is positive in the expansion of S alpha beta. But then we know by the rules of a base for a root system, if you have one weight on if you have one coefficient on the integer linear combination creating that root out of the base, then all of the coefficients are positive. Well, look, we've got one coefficient that's positive, meaning all the coefficients are positive. But that leads us immediately to S alpha beta is a positive root. So in other words, it's in R plus. And that's what we wanted to show for this lemma. Okay, so for our next result, let's suppose that we've got a root beta. Then there exists a g in W naught defined like this over here, and an alpha in B such that beta is equal to g applied to alpha. So in other words, every root vector is in fact an image of a basis root vector. Okay, so we're going to start off noticing that without loss of generality, we may assume that beta is a positive root. But it being a positive root, the argument here will be essentially the same thing as if it's a negative root, so we're okay there. Okay, then what does that mean? Well, that means that beta is equal to this sum over all gamma, which are base roots, where C gamma is bigger than or equal to 0, C gamma gamma. That's the definition of being a positive root. And now we want to define this accessory value here, and that's the height of beta. So it's some sort of measurement of the size of this root. So what it'll be is the sum over, well, the same thing as we had before, but now just the coefficients. So if we have a positive root, then the sum of those coefficients will most definitely be positive. And now we're going to perform induction on this height. And that's going to start with a base case. And the base case will be the height of beta equals 1. But notice that the height of beta equals 1, that means that beta is an element of B, an element of the base for this root system. But then we can write beta as simply the identity applied to beta. But the identity is most definitely an element of this subgroup of the Weyl group W0, like we talked about before. Okay, so now let's make our inductive step, which of course has to start with our induction hypothesis. So let's suppose for some k bigger than or equal to 1, every what I'll call beta naught inside of R plus with the height of beta naught less than or equal to k satisfies the condition. So I'll just put here satisfies here, but what I mean here is satisfies the condition. Just let's point that out, what that means. So in other words, there's going to exist something that I'll call alpha naught inside of B and G naught inside of W with, or W naught I should say, with G naught attacking alpha naught, giving us beta naught. So there's a lot of like subscript zeros there, but it is what it is. Okay, so now that we've got this, let's maybe make our induction step. This is like our induction hypothesis. So let's take a beta that's inside of R plus with the height of beta equal to k plus 1. So we've assumed up to k, now we're going to look at the k plus 1 case. Okay, nice. But now what we'll do is find a new vector gamma of the base with the inner product of beta with gamma naught, or maybe we don't need a naught there, with gamma strictly bigger than 0. So that's like a little geometric argument. Maybe I'll leave the reason why we're allowed to find such a gamma as a bit of a homework exercise. So let's point that out right here. So y is possible. Let's say it's homework. You can post in the comments if you'd like to. Okay, great. But now what we'd like to do is consider S gamma applied to beta. And we want to look at the height of that. So that's how we're like moving down for our induction step or whatever. Okay, so the height of S gamma applied to beta. So that's going to be the height of, recall that this is going to be beta minus this inner product beta with gamma in the gamma direction. So that's the way, or the definition, if you will, of this S gamma. But the height function is fairly clearly a linear function. So let's observe that that's going to give us the height of beta minus this wedge inner product beta gamma. Notice that gamma is one of the basis vectors, so we don't have the gamma there when we take the height. But now notice the height of beta is equal to k plus 1. We're subtracting something positive. So that makes this whole thing less than or equal to k. But if it's less than or equal to k, we can apply the induction hypothesis. And that's going to allow us to find something that's called alpha in B, so a basis root vector, and a G inside of W naught, where we have G applied to alpha is equal to S gamma applied to beta. But now all we have to do is left multiply by S gamma, keeping in mind that it's a reflection and thus its order is 2, meaning that we have beta is equal to S gamma composed with G all applied to alpha. And pretty clearly this S gamma applied to G is inside of W naught, because G was in W naught and then S gamma is also in W naught just by the definition of W naught over here. Okay, so let's maybe leave a kind of a related homework exercise on this board before we move on to our next result. And that is if alpha is inside of R and G is inside of W, then in fact G applied to S alpha, G inverse. So in other words, if you conjugate the reflection S alpha with G, you're gonna get the reflection in the hyperplane G alpha. Okay, so like I said, that's a nice homework exercise related to this. Now let's move on to our next result. So our next result is this little actually down here, which is W is equal to W naught. But we can actually prove this with our previous result. So let's take a generator S beta inside of W that may not be inside of W naught. So in other words, beta is inside of R. It may not be like from the basis. Okay, so now let's find G from W naught and then an alpha from B with beta is equal to G applied to alpha. So that's exactly from the previous result. So perhaps this should be corollary instead of lemma, but it is what it is. Okay, so now let's look at the following. So S beta is equal to S G alpha. But then by the homework exercise, that's G inverse S alpha G. But notice each of these three group elements are inside of W naught, meaning this whole thing is in W naught. Every generator of W is an element of W naught, but that's enough to show that W is equal to W naught. Okay, let's move on. So our next result is a kind of uniqueness theorem for a base of a root system. We don't have exact uniqueness. We have uniqueness up to maybe the Weyl group. Okay, so let's say R is a root system and we have two bases. Perhaps they're B and B tilde. Then the result is that there's an element of the Weyl group G such that G applied to B is equal to B tilde. Okay, so let's get right to it. So let's let B equal to alpha 1, alpha 2, up to alpha n. So that's our first base. And then, well, you know, very similarly, let's say that B tilde is alpha 1 tilde, alpha 2 tilde, all the way up to alpha n tilde. So well named. And then let's also set R plus minus equal to the positive roots with respect to B. So remember, you get positive roots with respect to a base of a root system. Those are not like necessarily fixed. And then let's set R tilde plus minus equal to the positive, and I guess I should be saying positive and negative respectively, roots with respect to B tilde. Okay, so we've got this set of positive roots and negative roots for each of the bases. And now we're going to do induction, and the induction is going to be on some strange number, and that number is going to be the cardinality or the size of R plus intersected with R minus tilde. So it's going to be the size of, well, the number of things that are positive roots in one that are negative roots with respect to another basis. Okay, so of course we're going to need a base case here, and the base case is going to be if this is an empty intersection. So in other words, we've got the size of r plus with r tilde minus is equal to 0. But let's notice that that is equivalent to saying that r plus is the same thing as r tilde plus. And that's because r plus and r minus are partitions of r. So if these do not intersect, well then just by a size argument, r plus and r tilde plus have to be the same thing. Okay, but then what does that tell us? That tells us that B is a subset of R tilde plus, and B tilde is a subset of R plus. And that's just because basis roots are positive roots, kind of clearly. Okay, but then what does that give us? So that tells us that, let's say we've got a root vector alpha j tilde. So since it's in B tilde, it's in R plus. But that means that it can be rewritten as the sum as I goes from 1 to n of these numbers aij times alpha I. So it's re-expressed in terms of the basis B. And this is important. So this is with aij are non-negative integers. Now we can put all of this together into a matrix, and maybe I'll call that matrix capital A, and that matrix is an n by n matrix with non-negative integer entries. And then we can do the same thing in reverse. So in other words, alpha j is going to be the sum as I goes from 1 to n of bij in the alpha I tilde direction. And here we're going to have bij are also non-negative integers. But that gives rise to another matrix. And that matrix is this bij matrix, which we'll call B. And again, that's going to be an n by n matrix with non-negative integer entries. And so let's also note the following, and that is that A inverse is B and B inverse is A, because that's just switching back and forth between the two bases. Okay, but there's an important result that I'll leave as a homework exercise. It's really just a linear algebra result that says if you've got these pairs of matrix inverses, or matrices that are inverses of each other, and their entries come from z bigger than or equal to 0, that means that A and B are permutation matrices. So in other words, A is equal to this matrix made up of the vectors epsilon sigma 1, epsilon sigma 2, all the way up to epsilon sigma n, where sigma is an element of Sn, where those are just like vectors building the matrix. That's what it is to be a permutation matrix. But then immediately that tells us that our alpha j tilde is in fact equal to alpha sigma j. But that pretty quickly gives rise to an element of the Weyl group that makes all of this happen. Just keeping in mind that the Weyl group is a set of permutations on the roots. Okay, so we've got the base case taken care of. Now let's move on to the induction step. Okay, so now we're ready for the induction step, of course, starting with the induction hypothesis. So let's suppose that the statement holds for all pairs where this intersection has k elements or less. And then now let's assume, well, towards the induction step, that the size of the number of elements in R plus intersect R tilde minus is equal to k plus 1. Okay, but then if that's equal to k plus 1, then that means that R plus cannot be equal to R tilde plus. Remember that those two things being equal was equivalent to that intersection being equal to 0, which it's not now. But now that pretty quickly tells us that B, because it's contained inside of R plus, is not a subset of R tilde plus. But if it's not a subset of R tilde plus, well then that means that the intersection of B with R tilde minus is non-zero. And well, that's what we're going to use as kind of our toehold. We're going to take some alpha from this set, which we just argued was non-empty. And then we're going to look at the reflection associated to that alpha. So in other words, we're going to set S equal to S alpha, and well, notice that that's most definitely an element of the Weyl group. Okay, so now let's consider the following set. And this is going to be S applied to R plus. But notice that those are going to be equal to the roots from R plus with alpha being sent to minus alpha. Let's also observe that these are going to be positive roots for this kind of strange set S attacking B. So that's going to be, well, another basis for this root system. Okay, and then, well, let's also note the following, and that is the size of SR plus intersected with R tilde minus is equal to K. And that's because, well, we've removed this alpha from this setup. So if we remove this alpha, well, that's one of the things that we've removed, meaning that we've removed 1 from K plus 1, making K. Okay, and then we'll apply our induction hypothesis. So that means that there exists something that we'll call G naught, which is in this Weyl group, such that the following is true. So G naught applied to SB is equal to B tilde. So again, we're like kind of running this for this other basis SB. Okay, but then next up what we'll do is set our G equal to G naught applied to S. So that's just a composition of elements in the Weyl group. And then let's note that that essentially finishes the whole thing off. Notice that G applied to B is equal to B tilde. And that's by this rule right here. And that's a good place to stop.